Welcome back, and this is the second in the series of videos looking at the transition metals. And in this video we're going to be looking at the properties of the transition metals. So that's their ability to have variable oxidation states, their ability to form complex ions, to work as catalysts, and to form coloured compounds. So you're going to need your notes, and we're starting on page 6. So the first of these properties is this ability to form variable oxidation states. So metals in groups 1 and 2 only have one oxidation state, +1 or +2. Non-transition D-block elements such as zinc and scandium also only have one stable oxidation state. However, transition metals have a variety of oxidation states, and generally speaking it's very easy to interconvert between these two. And generally speaking, it's very easy to interconvert between these oxidation states. Some of these oxidation states will be familiar to you, such as the manganese +7, which is found in the manganate ion MnO4-, or the +6 chromium oxidation state, which is found in Cr2O7-2-. The ones in bold are the more stable ones. So generally speaking, when you're using dichromate, it will go from the +6, that orange state, to a +3, which is the green. Sometimes you'll see it going to +2, which is that blue state. Another good example is iron. You're generally familiar with the +3 or the +2 oxidation states, and those are quite stable, but iron could be in +4, +5 and +6 oxidation states. And this is important within biochemistry. The other group which shows variable oxidation states is group 7, the halogens. With the exception of fluorine, halogens can produce ions of -1, +1, +3, +5 and +7. Fluorine, on the other hand, only has a -1 oxidation state. Do remember, oxidation states is the charge the species would have if the bonding was 100% ionic. Looking at the oxidation states of these different ions in terms of their electron configuration, well, iron has the electron configuration 4s2, 3d6. When it loses 3 electrons, remember it loses the electrons from the 4s first, and this is why Fe3+ is particularly stable, because it has single unpaired electrons in each of its d orbitals. Fe2+ would have this pair back in this orbital, and that paired electron is relatively easy to remove, which is why Fe3+ is generally more stable than Fe2+. Chromium has 1 electron in each of the d orbitals and 1 in the 4s. Remember, chromium, like copper, is this odd one where it back borrows to complete the 3d. Chromium 3+ has lost 3 electrons. You always lose this one first, and then it's lost 2 from its 3d. So the next thing we need to know about transition metals is that they can form these complex ions. So if we think about a compound containing a transition metal like iron 2 sulfate, there is an ionic bond between the metal and the sulfate ion. However, when we get to higher oxidation states, the transition metal is covalently bonded within an anion, for example MnO4-. And these oxyanions are very important. So if we consider vanadium exists in 4 different oxidation states. V2+ and V3+ are quite straightforward and can exist on their own. However, once you get an oxidation state of +4 and above, there becomes a problem. The +4 ion would be very, very small and very, very polarizing, and therefore it wouldn't be stable. So as a result of this, anything higher than a +3 is not going to be stable, and it's only found in these oxyanions. So oxygen, because of its high electronegativity, can draw out the higher oxidation states of the transition metals. So the +4 for vanadium exists as VO2+, and the +5 exists as 2 different ions, VO2+ or VO3-, and you'll notice both of the oxidation states of the vanadium, and the last example is +5. If you think of some other ones that you've come across before, again, MnO4-, again an oxyanion where I'm stabilising the very high oxidation state of the manganese here, +7, by combining it with the oxygen. And the oxygen can draw out the very high oxidation state of the manganese. Another one to think about is dichromate, Cl2O7, 2-. Again, the oxygen is there to bring out the high +6 oxidation state of the chromium. However, when the D block compounds dissolve in water, they can become hydrated. The lone pair of oxygens on the water molecule can form a bond by donating its electrons into those empty 3d or 4s orbitals. Now, this type of bonding is called a dative covalent, with both of the pair electrons coming from one donor atom. And these water molecules are called ligands. So ligands are compounds or ions with a lone pair of electrons, and this is what we call a complex ion. So for example, when we hydrate iron 3 compounds, we get iron 3 complex ion. That is an iron 3 ion which has 6 water ligands surrounding it, stabilising it by forming dative covalent bonds. So we have our iron, our iron, Fe3+ ion, and we've got 6 water ligands, all of which are bonding in, using the lone pair on the oxygen to form a dative covalent bond. Notice that I'm drawing water slightly weirdly. I'm just making sure that it's the oxygen which is pointing towards the Fe3+ and not the hydrogen. And because this has 8 bonding pairs of electrons all bonding in, the shape is octahedral. And you should know that from your lower 6th work on shapes. So the Fe3+ ion, if you remember, has 1 electron in each of the 3d orbitals. What I can do when I hydrate it is I can push those electrons together, and then I can add in my dative covalent bonds from my water molecules. Now I can do that because I've got the available orbitals to do that, and remember this is bond forming, so this is energetically exothermic. So you need to be aware of the different types of ligands, and the 3 you need to be aware of are monodentate, bidentate and polydentate. So monodentate forms 1 dative covalent bond. They're only going to be able to use 1 of their lone pairs. Now quite often things have more than 1 lone pair. So for example, water here has 2, but it can only use 1 of those. Because if you think back to the shape, the bond angles here between these water ligands must be at 90 degrees because this is an octahedral shape. And because those bond angles are at 90 degrees, there's no way that the other lone pair can bend round to join in and come in at the Fe3+ at a 90-degree angle. However, when we're considering biodentate ligands, in other words, compounds which can form 2 dative covalent bonds, I've got a big enough gap, there's enough carbons here between the 2 nitrogen groups to be able for this group to bend round and still come in at a 90-degree angle. And again, here the angle again can be at 90 degrees. So here in this case, I can use both of these oxygens lone pairs because they can come in at the correct angle. The last type of ligand you need to be aware of is polydentate, something like EDTA, which is a 4- ion. And here I have 6 places that the compound can bond in. It can use its lone pairs on the nitrogens and the oxygens to form dative covalent bonds, and that makes a very stable complex. You should also be able to use your VSEPR rules from lower 6th to predict the shape of molecules. So for example, silver with 2 ammonia ligands is a linear shape. So we've got the 2 N nitrogens using the lone pairs to form the dative covalent bond, and the same with the copper chloride, the copper 1+. Most 1+ metals are linear. When you have a 4-coordinate complex, in other words, when you have 4 dative covalent bonds, you can form 2 possible shapes, either tetrahedral or square planar. So here we have the tetrahedral shape with the chloros, and we have the square planar with the cyanides. There's one very important complex ion that you should be aware of, and that is this one. So this is dichlorodiamine platinum. It's better known as cis or transplatin, and the cis version is an effective cancer drug known as cisplatin. So they both have this planar shape, but in the cis version the 2 chloro groups are on the same side, and in the trans version they're on opposite sides. And this is the effective cancer drug cisplatin, which you're going to study in the application of transition metals. With 6 ligands, we get this octahedral shape where the bond angles are at 90 degrees or 180 across there. When you have a biodentate ligand, such as C2O42-, you can get optical isomerism because the 2 mirror images are non-superimposable. Naming these complexes can get a little complicated, but there are a couple of rules that you need to be aware of. And the most important of these is the fact that some of the ligands are given common names, such as water is given the name aqua. Amine, A-M-M-I-N-E, is ammonia. Notice this is different from amine, A-M-I-N-E, which is an amine molecule. Don't get those two muddled up. And carbonyl, which is a CO. The negative ligands always end in O, such as fluoro, chloro, bromo, iodo, and so on. And we've got the prefixes mono, di, tri, and so on to indicate the number of different ligands. The last thing is that if the overall complex has a net negative charge, you switch to 8 on the end of it. So cobalt, chromate, dichromate, manganate, and so on. There are 2 special cases, and that is iron and copper. So negatively charged iron complexes are called ferrates, and negatively charged copper complexes are called cuprates. So the first of these examples, I've got 4 ligands and I've got 4 ammonia ligands. And if you remember, the ammonia has a common name, amine. So this is tetra, meaning 4. Amine, don't forget the double M, copper. And then we give the Roman numeral for the oxidation number of the metal. Now, because here ammonia is neutral, the metal has the same oxidation number as the charge of the complex. So this is tetraamine copper 2. If we look at the next example, we've got 4 chloro. So I've got, again, tetra, chloro. But this time it's an overall 2 negative charge, so it's tetrachlorocuprate, because the overall complex ion is negative, but the oxidation number of the copper is still 2+, so it's tetrachlorocuprate 2. Technically, these should be written without any gaps. We've just put the gaps in to make it easier to see. So, for example, here, hexa 6 aqua vanadium, because it's not a negative ion and it's a 3+ ion. The water is neutral, so the vanadium has an oxidation state of +3. We should also be able to go the other way, so going from hexa aqua manganese 2 to the formula, and for example hexafluoroferrate to the formula. The third of the properties of the transition metals is that they can form catalysts, and we're going to cover this in more detail in a separate pack. We're moving on to the last of the properties of the transition metals, and that is their ability to form coloured compounds. So we need to understand why, for example, something like copper sulfate is blue. So white light, which contains all the different frequencies, if we pass that through our solution of copper sulfate, it will absorb light from the red end of the spectrum. So this part of the spectrum is being absorbed by the blue solution. And the colour we see is this end, the part of the spectrum which is not being absorbed. So the reason that copper sulfate is blue is because it is absorbing red light. We need to understand why that is, how copper sulfate appears blue because it's absorbing red light. So we need to think about the electron structure of the D block elements. So we have our D block elements with our 5 orbitals in the D block. And at the moment, they're all the same energy level. But when you bond the ligands in, this causes the D orbitals to split into a higher energy levels and lower energy levels. And they'll have some electrons in them. And what the light will be able to do is it will be able to promote an electron from the lower energy to the higher energy. And it will do this and absorb some energy. And that, in copper sulfate, is where we absorb the red light. We call this D to D transitions. And those D to D transitions absorb energy. So there are my D orbitals, all the same energy level. As the ligands bond in, they cause this splitting of the D orbitals. Now sometimes it will split 3-2 and other times it will split 2-3 as it does in this case. Light of a particular frequency will be able to promote an electron from the lower energy to the higher energy. As we said, we call this D to D transition, and that's a very important phrase. So you can see here the plot for nickel sulfate. Now nickel sulfate is green because it absorbs very strongly in the reds and in the blue part of the spectrum, but it absorbs very little light in this green part, and that's why we see it as green. Whereas copper sulfate absorbs very strongly in the red part of the spectrum up here, and this is why we see it as a blue solution, because it absorbs very little blue light. And you can see here we've got different colours depending on the oxidation states, and you do need to learn these. So vanadium 2+ is lavender, and you'll sometimes see it written as purple, and then green, and then blue, and then yellow. Okay, and we're going to learn a little acronym to learn those ones. So you do need to know the formula and you need to know the colour for the different vanadium complexes. And you need to know what will cause the colour to change. So we have different fields, some strong ligand fields and some weak ligand fields. And this really just depends on how good they are at these ligands are at bonding in. Generally speaking, the stronger the ligand field, the more towards the blue part of the spectrum, and the weaker the ligand field, more towards the red part of the spectrum. Remember, the colour is complementary to the absorbed colour. So if I absorb very strongly in the red part of the spectrum, you're going to see blue. But the changes you can make which will change the colour is if you change the oxidation number. So the different vanadiums have different colours because they've got different oxidation numbers. We can change the shape. In other words, if I move from an octahedral to a tetrahedral, that will change the shape. And I can change the ligand. So different ligands, because they will bond in differently and cause different splitting of those d orbitals, will also have a different colour. So a common question is explaining why zinc 2+ and scandium 3+ are both colourless. So zinc 2+ has this electron configuration, 3d10 4s0. So it has a full d subshell. And because it has a full d subshell, there's no space to promote an electron to. So we say that there are no d to d transitions possible. Whereas on the other hand with scandium, scandium has the electron configuration argon 3d0 4s0. In other words, it has a completely empty d subshell. So again, there are no electrons this time to be promoted, no d to d transitions are possible. So on the next page we have some common mistakes when discussing orbitals and coloured ions and transition metals. So, for example here, why zinc ions are colourless. They did get a mark for saying that D has a full subshell, but they didn't get the second mark for saying that there are no D to D transitions. So that's 1 mark for that one. Explaining why zinc ions are colourless for the second answer is wrong. It's not that the energy level split corresponds to a frequency outside of the visible light spectrum. I think they've got it muddled up with magnesium in the flame colours. The third answer is the best one because they've mentioned the fact that it's got a full 3D subshell, and they've told us that therefore no D to D transitions are possible. So that does get the full 2 marks. In terms of the structure, this first 1 out of 2 scores 0. We're asked to show all of the bonds, and although they've drawn the water, they haven't drawn out the full structure. And we have to recognise that C2O42- is a biadentate ligand. The second answer here gets 1 mark for drawing out the waters, but again, miss the fact that this is a biadentate ligand, not a monodentate ligand. Another classic mistake is not being detailed enough in your answers about why zinc is not classified as a transition metal. This one didn't score the mark. It's not zinc, remember, it's the zinc ions, which doesn't have a partially filled d orbital, and again there's a mistake there, that should be d orbitals. The second example is a good example. It forms no stable ions with an incompletely filled d orbitals, so it isn't a transition metal. You need both of those for the mark.